So good morning everyone, I am Michael Istigli and today I'm gonna discuss to you the radial groundwater flow. So what is radial groundwater flow? So it refers to the movement of water towards a well in an aquifer, typically following a circular path from the well's center. So we have here the radial groundwater flow in confined aquifer and the radial groundwater flow in an unconfined aquifer. So the first one is in confined aquifer. So radial groundwater flow in an unconfined aquifer refers to the horizontal movement of water towards or away from a pumping well in a pressurized aquifer that is bounded above and below by impermeable layers. So when we talk about impermeable, those are the rocks that is not easy for the water to flow. The flow is typically analyzed under a steady state conditions using the TIM or TIS equation. So later on, we're gonna have a sample problem on TIM equation. So radial groundwater flow in an unconfined aquifer describes the horizontal flow of water towards or away from a well in an aquifer where the water table is free to rise and fall. So the aquifer is only saturated below the water table and the flow depends on the changing saturated thickness as water is drawn down during pumping. So radial flow to a groundwater confined aquifer. So we have here a figure, and to derive the radial flow equation for a well completely penetrating a confined aquifer, the figure will prove useful. So the flow is assumed two-dimensional to a well penetrating a homogeneous and isotropic aquifer. So the well discharge at any given point can be given as Q is equals to AV is equals to 2 pi r K dH over dr. R is equals to RW and H is equals to NO and R is equals to R. Some distance away from the well gives the equation. So this equation, Q is equals to 2 pi K small b HO minus HW over ln RO over RW. So the above equation is known as the equilibrium or TIM equation, which enables the hydraulic conductivity of the transmissivity of a confined aquifer to be determined from a pump well that fully penetrate the aquifer. If there are two observation wells close to the pumping well and the distance r of the observation wells from the pumping well are known, the Q of the pumping well is known, and the water level in the two observation wells HE and H are known, the transmissivity of the aquifer can be calculated by applying the following formula. So this formula, T is equals to KB is equals to Q 2 pi H2 minus H1 ln R2 R1, or the T is equals to K small letter b is equals to Q over 2 pi S1 minus S2 ln R2 over R1.
So let's proceed to the first example of confined aquifer. A well penetrates a 25-meter thick confined aquifer. After a long period of pumping at a constant rate of 0.05 m³ over seconds, the drawdown at distance of 50 m and 150 m from the well were observed to be 3 meters and 1.2 meters respectively. Determine the hydraulic conductivity and the transmissivity. So the formula that we are going to use is T stands for transmissivity equals Q over 2 pi times S1 minus S2 ln R2 over R1. Q stands for pumping rate, which is 0.05 meter cube over S, and S1 and S2 is a drawdown at distance, and the R1 and R2 is a 50 m and a 150 m. So to solve, let's just plug in the given values. T equals to 0.05 over 2 pi times 3 minus 1.2 ln 150 over 50. So after that, T equals to 0.05 over 2 pi times 1.8 ln 3. So the final answer is T equals to 0.05 over 11.3 3097 times 1.0986 equals to 0.004864 meter squared over S. So the last step is calculate the hydraulic conductivity, which is K over T over B equals to 0.004864 over 25 equals to 0.001946 meter over S.
So next, let's proceed to the four assumptions for applying the TM equation in the steady radial flow of confined aquifer. First, the pumping rate is constant and is pumped for a sufficiently long time to reach the steady state. Second, the observation well are close to the pumping well so that the drawdown is appreciable. Third, the aquifer is assumed to be homogeneous and isotropic of uniform thickness and infinite areal extent. Fourth, the wells penetrate the entire thickness of the aquifer and the original piezometric surface is nearly horizontal. So, these assumptions for steady radial flow in a confined aquifer is important because it ensures the theorem equation is valid. It means water flows evenly and constantly towards the well, allowing accurate calculations of aquifer properties like, for example, transmissivity. Next is the limitations of TM method in steady radial flow of confined aquifer. There are three limitations. First, two observation wells are required at different distances from the pumping well to measure the drawdown at given time after pumping. Second, pumping is carried out for a sufficiently long time to approach the steady state condition. Third, theoretically HW and the pump well can be one of the measurement point, but the well losses caused by the flow through the well screen inside the well introduces error so that the water level in the pumping well, HW, should be avoided. After that, in conclusion, knowing these assumptions and limitations ensures that the TM equation is used only in situations where it provides valid and reliable estimates of aquifer properties. Misapplying it can lead to the serious errors in groundwater management, well designed, and aquifer analysis. Next, in radial flow in an unconfined aquifer, there are three assumptions. First, the aquifer is unconfined and underlain by a horizontal aquiclude. Next, the well is pumped at a constant rate. Third, equilibrium has been reached. Example, there is no further change in drawing with time. The next reporter will discuss more about the radial flow of unconfined aquifer.
So we all know what is the difference between unconfined aquifer and confined aquifer. So let's proceed to the unconfined aquifer on its formula. So the figure shows a well completely penetrating an unconfined aquifer. So makita nato dira sa figure kung saan ang flow niya sa unconfined aquifer. The well discharges is given as Q equals to negative 2 pi R times big letter K H times dH over dr. The previous equation, when integrated between the limits H equals HW at R equals RW and HHO at R equals RO yields. So mo yung formula, so ang Q equals to pi big letter K times H sub O to the power of 2 minus H sub W to the power of 2 over ln times RO over RW. Converting heads and radial to two observation wells, the above equation becomes Q equals to pi big letter K H sub 2 to the power of 2 minus H sub 1 to the power of 2 over ln times R sub 2 over R. So, dirita na ay tulo ka distinct phases ang drawdown. First is ang early. Water release from elastic storage follows this non-equivalent curve flow is horizontal. So, ang iyang flow kay horizontal. So, ang pangkadwa kay middle. Water table begins to decline. Water derived from gravity drainage. 3D flow, drawdown controlled by anisotropy of aquifer and thickness of aquifer. So, last is a late. Rate of drawdown decreases, flow is horizontal, and follows this curve with storability equal to specific yield.
So we have an example here. A well penetrates an unconfined aquifer prior to pumping. The static water level is 25 meter. After a long period of pumping at a constant rate of 0.05 meter cube per second, the drawdown at distance of 50 meter and 150 from the well were observed to be 3 meters and 1.2 meters respectively. So determine the hydraulic conductivity and the transmissivity. This is the formula for an unconfined aquifer, the TIM equation, where K stands for hydraulic conductivity, the Q is the pumping rate, H1 and H2 is the saturated thickness and distance, R1 and R2. First, let's find the difference in drawdown S and the ratio of the distance. So we have So we are just substituting the value in the given problem. Now we can plug these values into the TIM equation and solve the transmissivity. So solving for the transmissivity. For the T, we have 1.8 meter is equals to per seconds. So we are now gonna rearrange the equation to solve for the T. So by rearranging that will gonna be T is equal to 0.05 meter cube per second all over 2 pi 1.8 meter and 3. Now let's calculate the value of the T. M3 or LM3 will gonna be 1.0986. You can use your calculator to get the value of that. I put meter cube. No, per second. So RT will gonna be 2 pi times 1.8 11 point 3097 times 1.0986 meter squared per second. So calculating that one, that will be T is equals to 0.004421 times 1.0986 so we calculated that to get that 0.004421 times the 1.0986, that will be, the T will be 0.004857 meter squared per second. Yeah, so the transmissibility of the confined aquifer is approximately 0.004857 meters squared per second. So next, we can find the hydraulic conductivity, the key, using the relationship T is equals to Kx small letter b, because in the problem we have to determine the hydraulic conductivity, but we are done getting the transmissibility, so we have the hydraulic conductivity. So to get that, where our B is the thickness of the aquifer, so we know the T and B, so we can solve for K. So next, we're gonna rearrange the formula. So that will be K is equals to T over B, where our K is equals to the T, which is this one, 0.004857 meter squared per second, and over 25 meter in the given problem. We're gonna calculate it, and that will be, our K will be equals to 0.0019428 meter per second. To summarize, our T is equals to 0.004857 meters squared per second, and the hydraulic conductivity, the K, is equals to 0.0019428 meter per second.